Okay, we've got this truss problem, and hang on a second. So we have a truss problem with a 60 kilonewton force here at B, 3 elements, and reaction at A is a pin, reaction at C is a roller. Just to kind of connect it with some things we've talked about, is the truss stable internally? Yeah, it's a triangle. There's not much you can do with that. How about externally? Yeah. So we couldn't work an unstable problem anyway, but I just want to make sure that you kind of keep checking on that. Also, is it statically determinate?
Yes.
Yeah, we got 3 reactions, 2 at the pin, 1 at the roller. We have 3 bar forces, 3 plus 3 is 6. And we have 1, 2, 3 connections, 2 equations at every connection, 6 equations, 6 unknowns. So we should be okay. So what I want to do first is see if I can get my reactions. I think I can. So let's go ahead and I'll just quickly draw kind of a free body diagram of the structure. And I will assume at A that I have a force in the y direction and a force in the x direction. And then at C, it's a roller, I'll also assume a force. And then I have my applied force out here on the end. That's 60 kilonewtons. And all my dimensions are up here when I need them. So what should we do first here? Yeah, you can sum about A and get CY. You can sum about C and get AY. And then sum forces to get the other ones. I always like to sum at a pin, so I'll do that. So first I'll establish that I'm using right-hand rule for my sign convention, and then I'll write down that I'm going to sum the moments at A and make sure that's in equilibrium. So there's my statement of what I'm going to do. So now let's execute that. So just kind of moving from right to left, the first thing I see is CY. What kind of moment is that about A? Positive or negative? Positive. So I'll say CY times its moment arm, which is this distance, which was given as 5 meters. Any questions about that? That's pretty straightforward. Now we go out here and look at our applied force, 60 kilonewtons. It's acting down. That's going to create positive or negative moment? Negative. So force times distance. This moment arm will be this distance, which is 10. So it looks like CY is going to be 120?
Yes.
And I got a positive value, so I assume the right direction, which is really not that important right now. But so now I can sum forces in the y direction, so I'll assume up as positive. And I'm going to sum the forces in the y direction and make sure everything's in equilibrium. So I'll do that. So I've got AY up, CY up, and then 60 down. So positive AY, positive CY, and then negative 60. So when I solve for AY, what do I get? Negative 60. What does that mean? It means the force at A is actually down. Does that make physical sense? Well, if you think of C kind of as a pin, and this is kind of like a seesaw, if I'm 60 kilonewtons on this side, to balance it, you better be 60 kilonewtons down, or one of us is going to be in the air, and the other one is going to be sitting on the ground laughing at you. Isn't that the way it usually works with a seesaw? That's the way it worked for me. I always use the guy in the air. It's all right. You don't have to moan. It wasn't that traumatic. It's just, when you're 7 and you weigh 20 pounds, that's what you do. You end up in the air. Okay. So let's sum forces in the x direction. This one will be a challenging equation for us. Looking in the x direction, all I have is AX. Somebody calculate that for me real quick. What is the answer? -5? No, it's 0. Okay, so up till now, this is really just review. You should be pretty good at this by now. Even after the summer layoff, you're probably back in this mode, so you're okay. So now here's some possibly new stuff, but really review from statics. Which joints do you want to attack first in terms of solving for it? Let's do this. Are there any bad places to go?
No.
There's one. Well, let's just talk about A. If I go to A, how many unknowns do I have? 2. 2 bar forces, right? One of the bar forces is all X. One has an X and a Y component. So if I sum forces in the Y direction, I can get one equation and one unknown. What about at C? Same strategy. What about at B? Unless you rotate your axis, both of those bar forces will have X components and Y components. Unless you want to solve 2 equations and 2 unknowns, that's not a good place to start. So there's a little bit of strategy here. And I'll just, because A comes before C in the alphabet, I'll start with A. I'm a little corny, so this is my big joke for the semester. I'm going to draw my free body diagram. Are you ready? There it is. It's a point. Now what acts on the point? Well, I got my reactions at A. AY was down 60, right? AX is 0. Now I'm going to assume tension in force AC and tension in force AB. And while I'm there, I'm going to go ahead and note what I think this angle here is. And it looks like the slope of rise over run, right? So the run is 10, the rise is 5, so that's basically 2 to 1. That's my slope of that. And I'll use that to help me get my X and Y components. Is everybody okay with that? Okay, what should I do first? Some forces in the X or some forces in the Y? Was that WHY or just Y? You guys are not participating today. What's the problem? I'm going to call on someone. Who should I call on? Mr. Drum, who should I call on? He says Maxie. Maxie, what should we do first?
Y.
Some forces in the Y direction? And why would you do that? You don't know? Does anyone know why?
Because there's 2 unknowns in the...
If I sum forces in the X first, I'd get one equation in 2 unknowns. Not good. So let's do Y first. Okay, what is the Y component of this? Well, if you do Pythagorean theorem, the hypotenuse should be the square root of 5, right? So the vertical force should be 1 over the square root of 5. FAB. And it's acting up. And then I've got my 60 kilonewton force acting down. So I should be able to solve for FAB. It looks like it's going to be positive, and I don't know what 60 times the square root of 5 is. 130 something?
134.16.
134 point what, Mr.
164.
16. Well, I'll just say 16. Now I know mastering engineering tells you how many significant figures to enter, right? I think if you enter too many, does it count it wrong?
Yeah, it depends on if you're close or not. If you're close, it counts it right.
Okay.
I know, I read it somewhere in the book, and it was true in the statics book. Keep 4 significant figures.
Well, in structural mechanics, we say 3.
I thought when you do your calculation, keep 4.
Oh, well, your calculator has is all you want. You really only need to report 3. Because really, if the force is 134, what's the big difference? Is 134.1.
Right.
Not a big deal. It's 1,000th, right? And really, remember, the forces usually applied to a structure have been safety factor has been applied. So they're larger than what's actually there. So, whether you're off by a little bit, it doesn't really matter. Everybody happy with that? Does that make sense that AB should be in tension? I think so. When I pull down like this point A is going to try to move down and probably out a little bit, so it's going to stretch that. So tension seems to be reasonable. Okay, now that I have AB, I can now go back and sum forces in the X direction and find AC. So summing force in the X direction, I have the force in AC, the thing that I want, moving to the right. I have the X component of AB, which will be 2 over the square root of 5, the force in AB. And what else? Nothing, right? No other X forces. So I should be able to solve for the force in AC, and it looks like it's going to be 120. Or, is that right? Or think about it for a second. Yeah, 120? That makes sense? Is it positive or negative? Negative. So does it make sense that AC is in compression? Well, as I pull down on this, do you think C is going to move to the right or to the left? It's going to move to the left, so that means that AC is going to get smaller. It's going to compress. So compression seems to make sense. Hey, what do you know? We only have one unknown left. What's that? Well, I'll go ahead and mark it. I now know this one and this one, so I just need BC. So where's the best place to go with one equation to find the force in BC? I say C. So we go to joint C. Draw my free body diagram of C. Still not working. Do my CY force, which I found to be positive 120, and I assumed it to be up, so I'll apply that. And then my forces. So I always assume tension. So there's the force in AC, and then there's the force in BC. And looking at BC, what's the slope of BC? As a run of 5, a rise of 5, that's basically 1 to 1. So I'll just put that as 1 to 1. Now, even though I know AC was negative from my previous things, I'm not coming down here and messing with it. I'm just assuming tension. I'm going to write my equations with that. If I then need to use AC, I'll enter it as a whatever the value is, in this case negative. So how do I get BC with one equation, one unknown, and maybe not include previous calculations? Some forces in the Y direction. So if I sum forces in the Y direction, make sure I'm in equilibrium, AC does not contribute. So my Y component of BC would be 1 over the square root of 2. Square root of 2 is the hypotenuse. And that is BC acting up, and also acting up is the 120 kilonewton reaction force. So when you solve for FBC, you should get negative and whatever 120 times 1.4 is, square root of 2. 168, I'm guessing. You have calculators, don't you?
69.7.
169.7.
What was your guess?
168. It was just a guess. And we're done. Any questions about that one? Now what I could do, if I wanted to end this formally, is I could say, okay, the force in AB, let's see, AB is that. So I'll say that's equal to 134. Maybe I'll apply my 4 significant figure rule here. And that is in tension. The force from A to C is 120 kilonewtons, and that is in what? Compression. And then the force in BC is 169.7, and that is in compression. So at this point, it doesn't matter what I chose on my free body diagram. I should be able to hand this to any engineer, and they should understand tension and compression. So if you're a design, what was yeah, we hope. So he or she can now look at tension and say, oh, okay, I know how to handle tension. Maybe we can use a cable there. Maybe we can use a thin rod there. But these two compression guys, I got to do something different. I got to worry about buckling. And when buckling gets involved, you have to worry about the cross-sectional area and how it's arranged. You might remember from statics, the moment of inertia becomes very important for buckling. So if you look at a truss and you see really large members, those are probably going to be in compression. If you see really long, skinny members, maybe even rods or cables, you know those are in, because cables don't do good in compression. I've tried to push stuff with a rope and it just doesn't work. So any other questions? Okay, I'll stop that.